So I'm writing the content of whatever was taught this week. Lecture 4, which was about 1 hour long, 1 hour and 5 minutes. In that, it was linear and angular velocity of rigid body. In that, first there was introduction, where first notations were discussed. We will revisit this notation because today we will be using it extensively. Notations for right hand coordinate system, then it was a recap of notations as well as orientation. So orientation, we learned that 6 quantities are required with respect to a coordinate system. So after that, we had a short recap of homogeneous transformation matrix. So that means it is position as well as orientation. Then after that, after covering the recap, we move on to linear velocity. So in linear velocity of rigid body, we learned that there are 2 coordinate system involved. One by which we differentiate and other by which on which it is described. And after that, we talked about angular velocity of rigid body. In that, we specifically saw that of rigid body. In this, we specifically saw that angular velocity cannot be obtained as a time derivative of 3 quantities, let's say Euler angle, representing the orientation. So as example of position vector, if we just differentiate it, we get the velocity, but that doesn't happen in case of orientation. In orientation, we actually had to make a matrix. So angular velocity from time derivative of a rotation matrix. Hello? Sorry, my speaker was not on. Hello? Please raise your hand if you have any doubt. So angular velocity from time derivative of rotation matrix. So instead of orientation, the description of orientation, for example, Euler angles, we have to make time derivative of rotation matrix. Now that is interesting because it opens up the field. Hence, we have to jump to now skew symmetric matrix. Skew and what does that do? That gives us the angular velocity in term of the um, Euler angles. Okay. So now there are two type of system. One is space fixed, another is body fixed. So it depends on which symmetric matrix we are taking. If we are taking R dot R transpose, then it's a space fix, and if it's R transpose R dot, then it's body fix. So unless explicitly stated, space fixed angular velocity is normally used. Okay. After that, we had recap of angular velocity. Then we had recap of Euler parameter. So those are k, k hat, and there was phi. Okay. And finally, we had angular velocity in term of these Euler parameter. And this completed our lecture 1 along with the numerical examples. So numerical examples were will just write numerical examples here, and then in next page I will explain them. So there were 1, 2, 3, 4, 5, 6 numerical examples. In that, first one was first one was where a position vector was given which was changing with respect to time, and then linear velocity was asked. Okay, so we just had to differentiate each term. In second, the Euler angle with respect to time were given, and then we had to find the angular uh, angular velocity matrix. So it's a space. Okay, after that the third example was so second was space fixed. So this was space fixed. And then there was one example of body fixed. And then there was angular velocity using Euler parameters, where Euler parameters were given, and the task was to find the angular velocity matrix. So these are all good examples in which you can practically see how things are changing and what you have to find. Then there was position and orientation from velocities. So a linear velocity is given this time, and we have to find position vector. So a little trouble if there is no initial conditions. Okay, so if not mentioned, then we can take 0, 0, 0 as initial condition. And then finally there was task of obtaining the orientation if the angular velocity matrix is given. This thing was given, and what you have to find are these. So let me write what to find. So find, given, and then find. Find, find. So summary was summary of lecture 4 was um, position of a point on a rigid body is a vector. This means that linear velocity obtained by the differentiation of position vector with respect to time. So this was about linear velocity. And regarding the orientation, we know that orientation represented by three into three matrix for 3D, and then two forms of angular velocity vector was mentioned. One was obtained from skew symmetric matrix, R dot R transpose, and then this is called space fixed. Now there is another skew symmetric matrix also, which is obtained from again skew symmetric matrix, the same R transpose R dot, and this is body fixed. Then we saw angular velocity vector in term of Euler angle and Euler parameter. So that was lecture 4. All that was covered there. Now in lecture 5 had only one thing, this formula, these formula. The name was motion of rigid body and particles. And this is 1 hour 2 minute long. First of all, there was recap of lecture 4, and also which is actually equivalent to whatever I've said here. And then second topic was general motion of a rigid body. In that, this formula was given. We'll go in detail of this formula. So it's like a position vector. If there are two frames and one frame is moving, then how we can represent the quantities of interest from the frame which is moving to the frame which is at rest. Okay, so here let's assume if A is a frame which is at rest and B is a frame which is moving. Okay, then what will happen that due to the change of this frame, the quantities of interest will also change, and hence there will be some additional term because of the changing of that frame. Hence the position, then velocity, and then acceleration, it will have a compound effect on them. Since if position is changing and some additional quantities are there because of the frame change, then velocity will have more expanded version of that, and then acceleration will have more and more expanded version. So finally the acceleration terms were found out, and then each term was denoted by a text. So first of all, I will just color those. Let's go with the position first. Position is just the relative position. So if you remove the rotation part, if you take it as 1, then what happens that the orientation remains same, then it's just the relative position which we have learned in our basic kinematics, that x relative is equal to x1 minus x2. Then if you will see that velocity is nothing but v is equal to omega r when there is no change in orientation. So it is the generalized motion. Okay, and acceleration have now 5 quantities, and 3 of them we have already learned. So correlative acceleration we have learned, and centripetal acceleration we also learned. We have learned that tangential acceleration also. So if some angular acceleration is given, then that term come into the tangential acceleration. And then there are two, if frame is moving, the frame acceleration as well as the body acceleration in the rest frame. Okay. After that, after this, there was one AND problem, and on a rotating disc. We will be revisiting this problem. Okay. by a lot of angles to have more insight what this correlative acceleration is all about. And then there was then another numerical example. Then there was acceleration of a particle on the surface of Earth. After this correlative acceleration, we went to measure here two controls topics were there: MEMS gyroscope and MEM accelerometer. After that, we had some practical insight using Arduino. MPU 6050 accelerometer. So it was a demonstration. In that, first there was Arduino and MPU 6050 module connection. So it was straightforward. Then there was demonstration of the orientation. Followed by the acceleration demonstration. After that, yes, then calculating the position. Now that was challenging. So once you have the values of acceleration, now finding the position was little bit tough because the initial points were not known. So we had to assume here. So summary was, so already the summary which was there in lecture 3, that plus mm, okay, so positions and orientations can be estimated or in other word one can say by integration, by numerical integration of linear and angular velocities. This is tough, but yeah, this is the way. Then there were some off topic comments like the effect of correlations component. Resulting from the rotation of the earth is seen in many atmospheric phenomena. And today we will be talking more about these phenomena. It need not to be atmospheric. So today we will be looking at yes. So today we will be looking at lot of phenomena which is associated with correlations component, and some of them are really exciting. And then third, MEMS. Actually, MEMS are also um, based on this correlations component only. So gyroscope that gives the estimate of the orientation, and the accelerometer gives the estimate of the linear acceleration. Okay. Now moving on to, first of all, before jumping on to the 3D, I wanted to have the revision of the notations. The last time, which the notation which I used were slightly different, but this time we will be sticking to SURS notation. So first of all, coordinate system. It is shown by curly brackets. For example, if n is one coordinate system and its vectors we can show by n1, n2, and n3. So hat means unit vector. Similarly, one more example we can take is e, and it can be er, e theta, and e3. So it's like the cylindrical coordinate system, and n is like a Cartesian coordinate system. So now, if there is some quantity of interest, okay, let's say that is x. So x, first of all, there will be something here, and then something here, and also something here. So the leading superscript, so this is leading superscript, leading subscript, trailing superscript, trailing subscript. So this gives us that with respect to which frame, okay? So this gives with respect to. This gives like whose description it is. So let's say if it's written that some quantity is explained in E coordinate system and with respect to n coordinate system, okay? Then moving on, we have this thing explaining the point, and for now the trailing superscript means body fixed or the other one is space fixed. If nothing is given, then it's a space fixed. What I mean is, if some quantity is there, omega n e of p, then this means it's a space fixed. The vector of frame E with respect to frame N. Okay. Now to give more idea, let's take some frames as an example. So next topic is relationship between inertial and non-inertial frame. So let's consider S naught be inertial frame, which essentially means frame at rest. And S B, so we are using this terms, S B rotating frame with constant angular acceleration. Angular frequency, sorry. And what is that angular frequency? We can show it as S naught omega S of, so omega naught is that angular frequency. So constant angular frequency with respect to of what? Of S with respect to S naught. Okay. Now let's say, let us assume that Q is some arbitrary vector. So time rate of change of Q in frame S naught is related to its time rate. In S. How so? So S naught dq by dt is equal to s of dq by dt plus s naught omega s omega naught into q. So here it is defined with respect to s, and s of s is, we can write it like this only. Okay. So now instead of q, if we replace q by velocity vector b. Okay, yes. So all the vectors by this, so this is constant, so it's like scalar only. So instead of that, we can use that. Q is a vector. So if we do that, then we end in now R is also defined as R of S. Now if we differentiate it, then we get s naught a vector. So it's like acceleration with respect to s is given as s naught dr dt square of s is equal to s naught d by dt of this thing. Some things are missing, yeah. So this will end in that thing plus, so there will be some additional term plus s naught omega s into the same quantity. So what I did is I replaced q with a, and we got this thing, and this we can easily write as something which we are doing in the course. So one is this term, okay, which is nothing but the coriolis acceleration. Coriolis acceleration plus this is centripetal acceleration. Notation covered. Relationship between non-inertial and inertial. Okay. So let's solve a practical problem. Now we have an and on a turntable, same which was discussed in the class. Just read this question. So a turntable is rotating at a constant angular velocity omega naught about its fixed center C, and which is modeled as a point which is initially at 1, is walking along a radius of the turntable at a constant velocity v naught related to the turntable. Now the ant is currently at point 1 and wants to get to a nearby point 2. Okay, for reason it doesn't want to disclose, some personal reason. Now although omega naught and v naught are constant, we seek the acceleration of this ant relative to fixed reference frame, which is we denoted 0 xyz. So let's uh, first solve it by conventional method. So since it's a 2D problem, so we can put it on a plane and then we can make this geometry. And can you see the 1, 2 and 3 terms, 3 and 4 terms? So we will calculate that. So delta V radial is equal to this term 2 plus term 4 minus v naught. So what is this? This is new radial velocity. And this one was old radial velocity. Now this will be equal to v naught cos omega naught delta t minus omega naught r plus v naught delta t. Let me write it down next line. Then sine omega naught delta t minus v naught. So which in turns come out to be v naught minus omega naught square r delta t. Now everything is scalar, so no need of worrying about notations. Actually what we are doing, we are finding it by some other means so that we can have a idea of what exactly is going on here. So if simplify this using small angle approximation, so if we do that using small angle approximation, we get a radial first. What are those small angle approximation? Is cos omega naught delta t is 1 and sine omega naught delta t is equal to omega naught delta t. So if we do that, then a radial comes out to be limit from delta t to 0 delta v radial by delta t. Now if you will see in that form, then it comes out to be minus omega naught square r, and that we know is centripetal acceleration. Now doing it again for delta v tangential. Now we have term 1 plus term 3 minus omega naught r. So this was new tangential velocity, and previous one was old tangential velocity. So this we can write as v naught sine omega naught delta t plus omega next line plus omega naught r plus v naught delta t, and then cos omega naught delta t bracket minus omega naught r. Okay. which eventually simplify as omega naught v naught delta t plus omega naught r plus omega naught v naught delta t minus omega naught r. Now again simplifying using this time we get a tangential which again is limit from delta t to 0 delta v tangential by delta t, which is equal to omega naught v naught plus omega naught v naught to omega naught v naught, and this is our Coriolis acceleration. Now this is one way to go. Another method by we can solve is using what we are doing in this course. First we define the reference frames. So we have two reference frame, frame. First is S0, which is fixed, and then there is another rotating frame which is rotating with a disk. Okay. Now first of all we have to define the parameters. Now what is given is first angular velocity was given. So sign plays very important role here. Here S naught omega s, it becomes as minus omega naught k cap. You can use that clockwise notation of I, j and k, and we can say that it's coming to the k cap if there is no reference. So this is our reference, fixed reference. This is y, this is x. Now S naught a, this is written as d2r vector by dt square of s we have to find s, right? S naught with respect to, okay, so we have to find s naught and this s. So this comes directly as 2 omega naught v naught, pardon my omega, all scalars. Okay. Short break, 5 minute break. Okay. Let's continue here now. If you are afraid of the rotations, then I think next question is not for you. Lot of rotations are here. Just go through this question. So blood testing in a blood testing center, a batch of blood samples are processed automatically. Some chemicals need to be added to these samples. This is achieved by an array of three rotating platforms. Platform C rides on platform D, and platform E is independent of these platforms and carries a dispenser of chemicals which are electrically operated at proper times to dispense drops into the test tube held by C below. Okay. Now platform D rotates anticlockwise with a constant angular speed omega 1, which is 1.5 radian per second, and C rotate clockwise with an constant angular speed omega 2, which is 0.3 radian per second relative to platform D. Now we have to determine omega 3 for platform E if it is to dispense a drop of chemical having zero tangential velocity related to the test tube below. Okay. So what is given is, let me break it down to you. So there is a platform D which is slightly green, this thing. Okay. So platform D, it rotates counterclockwise with 1.5 radian per second. So counterclockwise. Okay. And platform C is D is this one, sorry. Okay, there is a color problem. This is red and C is this orange one. And then E, another is E is this blue green. Okay, so this is E, this is C, and this is D. D is rotating like this, and E is also rotating like that, but C is rotating with respect to so everything is mentioned here. Now we have to define the reference frame. So S naught is OXYZ, which is actually the fixed frame, and then S1, which is OX dash Y dash Z dash, that is for platform D. It is rotating invisible frame. And then S2 is rotating frame BXYZ, which is platform C, and it is by I2, J2 and K. See, K will be common in all three. IJ will change because it's again a planar problem only. And let's talk about angular velocities. So S naught omega S is equal to omega 1 k cap. This is one thing. Then next is S1 omega vector S2 is equal to minus omega 2 k cap. Just check if these two are correct, which is given in the question. If that is clear, let's move on to the main exercise, where um, S naught R of point A. Now A and B are point are given. So point A is so it's respect to S naught only. R1 I cap I1 cap plus R2 I2 cap. Now omega of S naught of S2 with respect to S naught will be equal to omega vector S1 plus S1 omega vector S2, which comes out to be omega 1 minus omega 2 k cap. So let me draw that ij and ijk. So this goes plus if this happens. Now S naught R dot or velocity is equal to S1 d by dt of R1 I1 cap plus S naught omega S1 into R2 no R1 I1 cap plus S2 d by dt R2 I2 plus S naught omega S1 S2 into R2 I2 cap. Okay, so here this thing and this thing are 0, so whatever is left is omega 1 k cap into R1 I1 cap plus omega 1 minus omega 2 k cap into R2 I2 cap. So this eventually comes out to be omega 1 R1 J1 cap plus omega 1 minus omega 2 R2 J2 cap. And if we put the values, then it comes out to be 1.14 J meter per second, J cap meter per second. Now we know that this is S naught R dot A is equal to omega 3 k cap into minus R3 I cap. So we have now this is known, we have to find omega 3, which comes out to be minus 1.9 radian per second. Okay, so this gives us the constant angular velocity at which E is moving. Now next is kinematics of a canadarm of a shuttle. Now let me explain what canadarm is. So a canadarm is a series of robotic arms that were used on the space shuttle orbiters to deploy, maneuver, or capture payloads. So it is always paired with an orbiter boom sensor system (OBSS), which is used to inspect the exterior of the shuttle for damage to the thermal protection system. A space shuttle has inbuilt canadarm and it is deployed to capture a slow moving small asteroid. And to do so, astronaut inside shuttle at position 0 needs to know the velocity and acceleration of the end effector S. Now there is a sensor on end effector to check movement of A with respect to S. What is the motion of point A as seen by the observer fixed to S? So that is our question. So first of all, we will see the figure. So inside that space shuttle, this kind of abstraction is there, and we need to find the, so this is an effector, and this is where astronaut is sitting. Now let us define frames here only. So reference frames n, which is equal to n1 hat, n2 hat, and n3 hat. Then we have E coordinate system, which is ER, E theta, and n3 again. If you have not realized, this is again a 2D problem only. Maybe we can do 3D maybe from today, or maybe we can have it done by next week. Okay. Now S is SR, then S5, and then N3. These are the reference frames, and angular velocities which we know of here in this question are E. Let's talk about E first. So this is given as theta naught n3, and this is given as phi dot n3. So these are the quantities which are given, and these are the reference frames which we are taking. So two things from which we can start our whole process. So let's find out first omega. What we need is this, which is equal to nr dot s is given as now this thing becomes 0 and this thing becomes 0. So L dot n1 vector plus theta dot n3 vector into r e r phi dot plus theta dot, the value which we calculated before, n3 vector into r s r like this, and then this eventually comes out to L dot n1 vector plus r theta dot e theta at plus r phi dot plus theta dot, and this is s phi. Okay, and accelerations of this s point, which is our end effector, is with respect to O we are finding. L double dot n1 vector plus r theta dot e theta vector r theta dot square e r vector plus r phi double dot plus theta double dot s phi vector minus r phi dot plus theta dot square er. Okay, and the last step, I think I'm not following the sign convention. Omega, then r, here vector will be there, here also vector will be there, fourth, and then here also vector will be there, vector. Okay, a the point is equal to s d by dt, s r a is equal to s and s omega vector e is equal to minus e omega s minus phi dot n3. S r dot a is equal to s d by dt Okay, so these are our solution. Everybody left the class. So just the addition or a generalization of this problem solving. So first of all, we have to find, so step 1 is to find frames, reference frames So in that there will be fixed coordinate system and then some moving coordinate system. Now next is quantities which you are given. So this comprises of angular velocities and angular acceleration. Angular velocities and angular acceleration. Then position vector, velocity, acceleration between two frames. Position, velocity and acceleration between two frames. Also position, velocity and acceleration with respect to moving frame. Next we have to apply the formulas. Position vector with respect to fixed frame, then velocity vectors with respect to fixed frame, and acceleration vector with respect to fixed frame. So kind of this is step 1 and this is step 2. But here I am missing an important thing, which is orientation. Now where the orientation will come? So wherever the quantities are, the orientation will be there. So orientation between two frames and orientation between moving frame. respect to moving frame. Okay, so after that, whatever is there I will keep in next class. So, okay, so this completes our lecture 2. We have still 10 minutes, 11 minutes left. So what we will do is we can talk about very small topic, cross product. Now that essentially means or let's do it in the next class only. Let me see if I have slide for that. Lecture 3. Yeah, we have just copy paste, cut, and last copy paste. So we know that I cap into j cap is equal to k cap clockwise. Okay, then j cap into k cap is equal to I cap, and then if we talk about j cap into I cap, so this become opposite, so minus k cap. And if some vector is there and we are cross multiplying with the same vector, then that becomes 0. And so in this notation, cross means outside paper, outside screen, and this means inside screen. So for example, if you want to find e1 into e3, that comes out to be minus e2 vector, and e2 into b3, that comes out to be cos theta b1 vector minus sin theta b3 vector into b3. So this comes out to be e2 as cos theta, and this is 0, and this is minus sin theta. Now e2 into b3, hence we can write as cos theta b1 vector minus sin theta b3 vector, this into b3, which eventually comes out to be cos theta b2. Why? Because b3 vector into b3 vector is 0, and b1 vector into b3 vector equal to minus b2 because of okay. Now what I will do is that I will make this as PDF and upload. So if we remove the template setting and then share PDF, okay. So So how many questions we have done? We started with question number 1, example 1, this, then example 2 was this, then example 3 is this. So three questions. And the revision. Normally I wanted to discuss doubts, but it's okay. So this Canada is somewhere here. Let me draw that Canada here, and then we will export it there. Some different color. So this is what I meant by Canada. Okay, time up. Bye bye. I'm stopping the